Welcome to a GitOps approach to ML and how Interos is building a world-class ML platform. So what exactly are we talking about today? Today we're going to go through the ML lifecycle and tooling needs and what they look like at Interos, the benefits and challenges of GitOps, and then we're going to go over what we keep in code, which includes onboarding, data, deployment, and monitoring tools. So at Interos, we're the see everything, do anything company. We use an expansive suite of AI tools to measure supply chain risk. I'm Stephen. You can see me there on the bottom right, also here on stage. On the top left is our team lead, Joseph Haga.
And I'm Amy. I'm a Senior MLOps Engineer. And Prasad, who couldn't be here with us today, is the latest addition to our team.
So this is what the ML lifecycle looks like at Interos. So first off, we onboard new models, then we can run experiments, we build them, upload them to S3, and then once they're live, we can serve predictions to them. Once those predictions are getting served, they go through our data feedback loop, and we can collect that new data to retrain those models. We also, of course, monitor those models throughout the entire process. So what we're here today to talk about is the beauty of GitOps. So GitOps is an operational framework that takes DevOps' best practices such as version control, collaboration, CI/CD, compliance, and applies them to automation. And this has multiple benefits, including increased productivity, enhanced developer experience, greater stability, consistency and standardization, greater security guarantees, and of course peer review through the use of MRs. So the main principles of GitOps, and we're not going to delve too deeply in this because I'm sure you're familiar with the basic concepts, are that you have engineers committing to a centralized repository that stores the current and past state of the application. You can make pull requests against the main branch or whatever release branches you want to use, and you can trigger off CI pipelines, which trigger CD pipelines, which you can automate various tasks, including validation, and at the end of the day, all of this is traceable. You can roll everything back, and everything is stored in code.
Okay, so the challenges of GitOps. So not to discourage you from implementing GitOps, but we did come across a few hiccups when implementing that into our ML lifecycle. But we did find that the benefits of GitOps outweigh the drawbacks. So we're here to advocate for it. But we're going to go over a few challenges that we've come across. The first one we have here on the list is how do we apply GitOps to GitOps tools? We have found that GitOps tools are not actually promoting GitOps principles. For example, do we have any Argo CD users here? Flux? Okay. So we have a few Argo CD users. So Argo CD and Flux are two of the most popular GitOps tools in the market. So if you look at their installation instructions, they do not instruct us to have something defined in code and checked into Git before applying the changes to our cluster. Now, that stuff has improved. Now, almost all tools will give you some kind of a declarative YAML file type of installation. And you can check that into Git and hook it into your CD tool. But they still refer you for the initial deployment to run things like kube control apply and Argo CD add, which negates the principles of GitOps. The second bullet point I have here is what is running in the cluster is very different from what was defined. So I'll give an example to clarify this bullet point. Any Kubeflow users here? Okay, just one. Wow, okay. All right, I expected Kubeflow to be a little bit more popular than this. But take, for example, if you were to deploy a model using a Kubeflow inference service. And for those of you who don't know what Kubeflow inference service is, it is just a Kubernetes CRD that facilitates for you to deploy a model on a Kubernetes cluster and serve it through an endpoint. Kubeflow inference service is actually quite simple. You can, through a few lines of YAML code, define your inference service definition, which means how to deploy your model. And then Kubeflow inference service basically goes out and creates a bunch of other objects. Those objects, some of them are like SU networking components, and others are Knative serving components. But those objects are now nowhere to be found in code. They are not in Git. So Git is no longer the source of truth, and therefore we have the problem of what is running in the cluster, the actual state, now differs from the defined desired state in Git. And this, again, negates the principles of GitOps. Immature observability. Well, this is actually one of the main pain points we have experienced at our team. Having to navigate multiple tools to trace back a change to its source. Again, I'm going to talk about Argo CD because we use that to deploy our models into our K8s clusters. It provides a link to the commit that initiated the change to the actual state, but it doesn't really link you to a pull request or a merge request that initiated that change. And also, you'll find yourself looking for the Jira or GitHub issues and tickets that caused you to create the change in the first place. Also, you'll be wondering, where is my CI pipeline run that caused the CD pipeline run, which triggered the deployment and the change in the first place? So to answer all these questions, you'll find yourself going from one tool to another and from one repo to another, which could be very frustrating. The last challenge I have here on the list is we need universal GitOps patterns. Now, GitOps principles are actually quite simple and straightforward. So everything needs to be defined as code. Code is stored in Git. Git holds the desired state. And then machines converge the actual state into the desired state. But if you look at the GitOps tools in the market, they leave so many questions unanswered. For example, how do we determine when we use a push versus a pull mechanism? How do you organize and define your environments? Should you have all your environments in one repo? Or should you define one repo per environment? Or maybe you should use branches for your environments. How do you implement things like manual approval process in an automated CI/CD pipeline? You'll find yourself wondering, what are the good practices of GitOps? Now, there are a few tools out there that attempted to define some good practices, like Jenkins X, if you guys have used Jenkins X before, in Flux. But those implementations don't work outside of those tools. So we have found that we really need some universal GitOps patterns that can be applied no matter of the tooling being used. Okay. So how do we do GitOps at Interos? We implement GitOps in the entire ML model lifecycle, from onboarding all the way to monitoring and data feedback loop. Everything is in code, and everything is GitOps driven.
And so we're going to start by talking about our onboarding process. So at Interos, we have one onboarding tool called our boarding pass, and we also have a repo with our model project templates. So what boarding pass does is it is a set of automated processes that are stored inside one centralized repository. When you want to run a pipeline, it kicks off all of these automation scripts that can create our model artifact storage, our model repo, integrations with Jira and Slack, our monitors and Datadog. And when you want to kick off this process, it looks a bit like this. So typically an ML engineer might file an onboarding request with our team on Jira in Service Desk. We can just copy and paste those values that they enter in the onboarding request into this pipeline and hit run pipeline, and it creates everything we need. This has reduced our deployment times or our onboarding times from hours to a matter of minutes. And when we create that model repo, this is exactly what we're talking about. So we have a cookie cutter project that is our model project template. And we actually have multiple branching templates for every different kind of model you would want. But our basic one includes a folder for data sets, labels, weights, tests. And all of this is, we have tools to make sure that it follows this structure, and those will be open source soon. But anyways, as I was mentioning, the model project template is critical because it provides this common interface that we can use for servicing those ML models once they're live. We also use GitOps approach for data. So we're actually using data version control for automatic versioning of our data and building simple data pipelines for our ML engineers. So if you aren't familiar with DVC, and this image is taken directly from the DVC website, so it works a bit like Git. But the data itself isn't stored in Git, only the version of the data is. So when you revert a commit, you're actually reverting to a previous version of the data. And DVC also allows you to create data pipelines. These can actually automate many tasks that we would want to run for data. And we can even kick those off inside of our GitLab CI/CD pipelines. So the process for ML engineers at Interos essentially looks like this. ML engineers can commit changes to their data set locally in their model repo. They track those changes to their data. They push that data to Git. And then when they push that data to Git, it actually triggers pipelines, both in GitLab and DVC, that can upload that data to the cloud and do whatever we need to do with it.
All right. Well, now that we have seen how we apply GitOps principles to model onboarding and data, we're going to also talk about how we apply the same principles to model building, deploying, and monitoring. Okay. At Interos, we use Argo CD as our main deployment tool, and we use Kubeflow deployed on Kubernetes clusters as our model serving platform. Now, Argo CD, for those of you who don't know, it's a declarative GitOps tool for continuous delivery on Kubernetes. This is how it works. Basically, you define the desired state of your model's deployments in a Git repository, and then you hook up your Argo CD deployment to that Git repo and also to your Kubernetes cluster, and then you just let Argo CD sync the actual state in the cluster to your defined desired state. And this is what a typical model CI/CD pipeline looks like for us at Interos. So an ML engineer makes code changes, and they commit their code to a model repository. And then we have a CI pipeline triggers on the model repo, which basically just builds the model, tests it, and then push a Docker image for that model. We automatically push to our dev environment. But on higher environments like staging and prod, we open up a merge request where we allow for a manual approval process to happen according to merge request approval rules. And then once the merge request is approved, it is merged, and that pushes the model to higher environments through Argo CD sync. Okay, now let's dive deeper into how this all works. And hopefully you can all see this diagram. The font is a little bit small. Actually, before we do that, I did mention a model repository and an environment repository. So what is the difference between those two? The model repo, and that is in step number 2 over there. The model repo contains model code. What is model code? It could be anything like training and serving code. And the environment repository is a different Git repository. And that one contains environment-specific configurations for model deployments. That could be something like an Argo CD app YAML file. At Interos, we have hundreds of models. Typically, we have 1 Git repo per model. And we have 4 environments. And that corresponds to 4 environment Git repositories. And we have 2 Kubeflow clusters. We have a prod cluster that holds the higher environments, and then we have a lower cluster, and that holds the lower environments. Okay, so looking at the top left corner with step number 1, an ML engineer makes code changes to the model repo. That could be anything like a serving code change or maybe a model weight changes. And they commit their code to the model repo. That triggers a CI pipeline on the model repo. That's step number 2. It uses the model weights from S3 to build the model, test it, and then it packages the model in a Docker container and pushes that into our Docker registry. Like I mentioned, we automatically push to our dev environment, which means we simply make a commit to our dev environment repo. But for a higher environment like step number 3, like a staging environment, we actually open a merge request, and we wait for the stakeholders to approve that merge request. The stakeholders could be either the QA team or maybe the release manager. Once approved, the stakeholder merges the merge request, and that is step number 4. And then Argo CD syncs the actual state of the model to the new state, and that is in step number 5. And if the merge request is not approved, the stakeholder could simply close the merge request to cancel the deployment. So now that we know what an environment repo is and how we can use it to achieve the desired state for a model's deployments, what if we have tons of environments and we have hundreds of models running in those environments and they get updated all the time? How do we guarantee that the basic model configurations are the same across all our environments and all our models? One way to do it, we can probably create a common YAML configuration template and just copy-paste that template into all our models and all our environments. But then what happens when you have an updated version of that basic configuration? How do you propagate that updated configuration template to all your models and ensure they're all using the same most recent version of that template? So this is how we solved this problem at Interos. We created, one slide back, please. We created something that we called an environment repo template. That is a separate Git repository where we keep the basic model configurations for all our models. And we do that through a parameterized YAML template. In our case, all our models are Kubeflow inference services defined through a Helm chart, and we allow customization to our models through Helm values. So looking at the code sample we provide here in this screenshot, you can see that some example of model basic configuration could be the model Docker image. We have some environment variables. And we also have some deployment resources, lines 38 through 46. An example of that could be allowing a custom configuration to the CPU and memory limits and requests of the deployment. Okay. And this is an example of a specific model configuration. In this example, it's the staging environment. I want to draw your attention to line number 19. So as you can see there, we are pulling basic model configuration from that environment repo template. And then on lines 39 through 45, we are applying some specific custom configurations to this model. For example, we're instructing the model here to be deployed on GPU. And we are specifying a CPU limit of 1500. Okay. So environment repos are great. But what if we want to automatically update a certain critical environment like prod, but we want to have a human check off on it at the same time? So how do we do gated deployments in GitOps? At Interos, we have repurposed merge requests on environment repos to achieve that. So anytime there's an update to any models in a higher environment, like prod and staging, we would open up a merge request on that environment repo, and we would send Slack and email notifications to the stakeholders. Now, we created approval rules on merge requests, and we use them as readiness checklists. For example, we have an approval rule for QA team where we require at least one QA engineer to review the changes and approve the merge request before we allow it to be mergeable. We also took advantage of the discussions features in a GitLab merge request, where we allow these stakeholders to ask questions about the merge request or about the change being deployed, have blocking conversations, and have documented communications. But once all the discussions have been resolved and all the approval rules have been met, the stakeholder can either merge the merge request to deploy the new version of the model to the higher environment, or they can simply choose to close the merge request, and that cancels the deployment. So now with this solution, deployments to critical environments can still be automated, but at the same time, they are now controlled, gated, and governed.
So lastly, we also use GitOps approach for monitoring. So at Interos, we like to monitor as much as we can, and we like to store, we use Datadog at Interos pretty heavily, and all of our dashboards and monitors for Datadog are actually stored in a centralized repo. We also store utility scripts and pipeline code in that repo as well. When you trigger a GitLab pipeline, it actually runs this to update all those dashboards and monitors and Datadog itself. Pretty nifty. You can see an example of a dashboard here that was updated by such a pipeline. So what are the takeaways of all of this? Well, faster everything, for one. As I mentioned before, we were able to decrease our onboarding times from hours to minutes. And it's not just onboarding that we saw an increase in speed. Our deployments as well. We increased our deployment speed and iteration speed dramatically, able to deploy on a daily basis, multiple times a day even. And there's also the benefit of traceability. We're a federal contractor, so everything needs to be auditable. And Git allows us to do this. We can see exactly who made a change, when they made it, and why they made it. And we can even trace that back to the very ticket that triggered them making that change. And then there's also CI/CD. So with GitOps, we were able to automate a lot of tasks that we would have to do manually otherwise. This is all contained in CI/CD pipelines, which has incredibly increased our deployment speed. And then lastly, and most importantly, I think, communication. GitOps has allowed us to achieve greater productivity, stability, and reliability across both our team and other teams inside of our organization through the use of peer review and merge requests. Lastly, we'd like to open it up to a Q&A, but before we do that, I'd just like to quickly mention that if you'd like to learn more about some of the tools that the MLOps platform is building, we do have our engineering blog at Interos Engineering. We also have some open source tools, and there's more coming, and you can find them there. Right now, it's just our GPU watchdog and multi-exec. And for any other questions that we don't get to, because we are on time, you can reach out to me at sbrown@interos.ai or amy@abachir@interos.ai. And before we get to the questions, there was one that we got on the app, so we'll address that one first.
Okay, so Santosh, I don't know if you're here, he asked a question, can we use GitOps in automating our infrastructure? So the answer is yes, absolutely. So this is the most basic use of GitOps. This is actually how it all started, is that automate the provisioning in infrastructure. So depending on the cloud provider that you are using to provision your infrastructure, you can definitely use the same exact principles that we just mentioned to provision your infrastructure. I've personally used and have seen a lot of companies use either Terraform, or if you're on AWS, you would use CloudFormation, and then you would kick off that provisioning from a CI/CD pipeline in your Git provider, whether it's GitLab or GitHub or Bitbucket. So yes, definitely. We didn't specifically want to talk about automating infrastructure through GitOps today because it's such a common and popular use case, and good practices are already established around it. We wanted to specifically talk about deployments in environment repos, which I surprisingly find that a lot of people aren't aware about environment repos and how they can use them in GitOps, specifically with Argo CD to sync your desired state defined in Git to your actual state in that cluster. But yes, absolutely, you can use GitOps to automate your infrastructure provisioning.
Yeah, so hopefully that answers your question if you're in the audience. If anybody else has any questions, you can just line up at the microphone here.
Can you talk a little bit about how does this handles failures, like deployment failures? What happens when part of the workflow fails? How do you recover from that?
So we work mostly in GitLab, and we can see all of our CI/CD pipelines that run. And if there's a pipeline failure, it can actually tell us the exact job, and we can look into that exact job and look at the actual traceback of the errors that were made. And we make sure that when we're building tools that we add sufficient logging so we can actually figure out what went wrong. Yeah.
So we mainly use Python and Bash in all our scripting. So two ways you can implement validations in failure handling. So there's one way to do it with, for example, GitLab. There are retries. I believe right now the retries you can have a max of 2 per job. So that's one way we do that. And then the second way is, your just good old try-catch exceptions through the programming language of your choice. And in this case, we use Python and Bash. So we implement that everywhere we think there is a failure. But obviously, some errors only reveal themselves when they want to. So as they happen, we continue to add logic. And it's really easy for us because everything is in Git. So anytime we come across a failure that we've never seen before, edit our scripts, add exception catching, and then we check that in, and then the next pipeline run, the issue is handled. But yeah, Git makes it very easy because you never have to guess, what that failure was. We create a ticket. Everything is tracked in Jira. That ticket defines what that failure is and how we plan to handle it. We link that to the merge request, which it's pretty nice when you actually link your ticketing system in the pull request, because as soon as you make a commit, it actually puts that commit message for you directly in your ticketing system. So everything is connected together and traceable through commits. So we can know exactly what failure scenarios we're trying to handle, why, and how we handled them, and who actually checked in the change in the fix for that failure. Sure. So the question is, we have introduced something that's called environment repos. And the question is, how are they used for experimentation and debugging? The answer is they aren't. So those environments are not actually for local development use. So we have a separate experimentation pipeline. We use Kubeflow notebook servers that actually run on the cluster, and engineers can develop directly in those Jupyter notebooks and have their own development environments. Or they can connect to them from their local machine. It's a really bad idea to have shared environments for development and experimentation because developers will be stepping on each other's feet. So the environments that we're talking about here in this presentation are more of target deployment environments where you've already done your experimentation on either your local, or for our case, we provide actually remote GPU-powered environments through Kubeflow notebooks. So you've already done that experimentation, and you have a candidate model. So you think this model would perform well in production, and you want to try it out. And those environments work like that. We don't deploy directly into prod. We try out the model in dev, and then we have regression testing. We have load testing that is actually performed in staging environment, which we're not showing now, but staging environment sits on the same cluster as prod. So we can do load testing and ensure that those models are going to perform well on the same infrastructure. And then we promote to prod. So any local development or experimentation is done completely outside of those environments. And you typically don't really want to necessarily have those environments configuration as code, like experimentation environments, because they are developer specific. You typically would want to use something like an experimentation tracking server. I don't know if you've heard of MLflow. So we do use that in our experimentation pipeline, and you can use Kubeflow's metadata, which is very similar to MLflow to log your experimentations. But yeah, it's not a very good idea to use like a dev environment as a shared development environment for all the engineers. I hope that answered your question.
Yes.
Go ahead.
So I just want to make sure that I got this right. So the final model that's trained, that's actually trained in your CI pipeline in GitLab or something, if you have Azure pipelines or AWS, whatever, but it's trained there and not in another platform and then pushed somewhere. Is that correct?
So as far as so what we showed so far is you have a candidate model that's been trained already, right? So your ML engineer has done the experimentation, hyperparameter tuning. They have a candidate model that they think they would like to deploy if it does better than the existing model. So all that has been done already in the developer working environment. Like I mentioned, we use GPU-powered Kubeflow notebooks. So when you get to that CI/CD pipeline, you already have a trained model with weights. We showed that we use S3 to store our weights. So we link that to our experimentations. We store the actual artifact, the weights, in S3. So the start of that CI model starts with a candidate model that's been trained already and hyperparameter tuned.
And then just one follow-up. Is there any validation on the Docker containers as well?
Yes, of course. I'm glad you asked this question. We love validations. We have lots of testing. We didn't mention this here because we think that it's a given that you should test your models. But our CI pipeline has plenty of testing. So we have unit testing.
It's mostly test.
It's mostly testing, yes, because at this point you've already, you trained the model, you have the model artifact, but it's mostly testing. So we have some compliance checks to make sure that, our engineers have followed the standards, the common interface that we asked them to program against. And then we have linting. We have unit testing for each and every function, like serve.py, for example. And we also have integration testing built into our CI pipeline, where we have ephemeral environments. That's actually a core concept in GitOps. We have an ephemeral environment that we stand up just for the duration of the build. We completely deploy the model on an endpoint that is actually ready to serve requests. And we send a smoke test to it. And then if that smoke test returns a good response, then that integration test passes. Otherwise, we actually fail the build, and we block our engineers from deploying even to dev environments. So we can catch errors and failures as early as possible in the lifecycle.
Just a follow-up on the experimentation part. I know it's maybe it's out of scope, but are you also using GitOps for experimentation? So let's say we know that ML is research-driven. So probably we're not going to hit the best experiment in the first trial or the last one. So is there any way to revert back to previous experiments? Are you using just Git and DBC, or are you containerizing everything? So what is your approach there?
So as far as experimentation, I personally don't think it's a good idea to use GitOps for experimentation because it's a lot of trial and error. We do use experimentation tracking, though. So it's up to the engineers to check in their changes to their code for their experimentations. But we do track, we ask them to use a common experimentation pipeline that records all their training parameters, hyperparameters, metrics. Everything gets recorded to MLflow, and then we're experimenting with the Kubeflow's metadata as well. So it's not quite GitOps, but there is tracking through experimentation tracking servers like MLflow. So not 100% GitOps, but there's definitely some sort of tracking. You wouldn't want to revert an experiment. You would want to potentially compare experimentations. You wouldn't want to revert, you just run an experiment and you record it. And you can run the same experiments and have multiple runs for it. For example, parameterize your hyperparameters, and then feed in different parameters and run the same experimentation multiple times. But there isn't really the concept of reverting an experiment. It's a one-time run. It's recorded in history. You can always go back to it, look at it, and things like MLflow tracking server makes it very easy to do this compare. But yeah, not 100% GitOps, but there is a GitOps concept in the fact that it is all tracked and everything is recorded in MLflow tracking server.